So next we want to use Simpson's rule to approximate our integral from 0 to 1 e to the negative x squared. With Simpson's rule, the idea is to divide your interval AB up into an even number of subintervals, and then you cap each pair of subintervals with a parabola instead of a straight line. So for example here, we want to estimate using Simpson's rule with n equal 4. So 0 to 1 here, our delta x is going to be b minus a over n, so 1 minus 0 over 4, which is 0.25, 1/4. And so our x0 is at 0, and then 1/4, 0.25, that's our x1. X2 is at 0.5. Our x3 is at 0.75. And our x4 is at 1. So what you do is you've got even number, and then you take each pair. So this first pair of subintervals, what we're going to do is we're going to take that and we're going to cap it off with part of a parabola. So above the point 0, we've got a point on the graph here. Above 0.25, we've got a point on the graph about right there. And then above 0.5, we've got a point on the graph right there. So there is a unique parabola determined by those 3 points. So just like there's a unique line determined by 2 points, there's a unique parabola determined by 3 points. And that parabola might look, something like this, for example. And so that would be the unique parabola that goes through those 3 points. Now I know I drew it so it doesn't quite go through that third point. I'm trying to illustrate it's part of a parabola. And then we do the same thing for this pair. So you've got 3 points on the graph here, determined by the function value at 0.75, and then the function value at 1. There's a unique parabola that goes through those 3 points. And, maybe that parabola looks like this. Kind of hard to draw this. Yeah, well, I was going to say something like this. So you get the idea. It's going to be the straighter portion of the parabola, out towards the end, not the more curved portion. This up here looks like it could be the more curved portion. So that's kind of hard to draw by hand. Wolfram demonstrates it a little bit better. So here's our Simpson rule with n equal 4. So these two subintervals are capped off. That determines 1, 2, 3 points, and that is part of a parabola. And then these two subintervals, 1 to 1.5, 1.5 to 2, determine 1, 2, 3 points, and then this is part of a different parabola determined by those 3 points. And then you find the area underneath the parabolas. Now the approximate area, the shaded area here, 1.41665. And look, the exact 1.41615. So our error is very small, 0.0005. And as you take more pairs of subintervals that are capped by pieces of parabolas, our error goes to 0. So look here, we're at n is 16. Our approximate area now agrees to 5 decimal places with the exact area. So Simpson's actually the most accurate rule of all of them. It's also a little bit more complicated to compute, but not too bad. So we want to do Simpson with n equal 4. So we start, S is for Simpson, n is the number of subintervals. So we'd start with delta x over 3. So our integral from 0 to 1 e to the negative x squared dx, which can be approximated by Simpson's rule with 4 subintervals. And this will be our delta x divided by 3, so 0.25 over 3. First function value has no multiplier, so f at 0. And there are going to be 1, 2, 3, 4, 5 function values. So the ones in the middle alternate with a 4, 2, 4, 2, 4 pattern, and then the last one has no multiplier. So this will be 4 times the function value at the second endpoint, so 0.25, plus 2 times the function value at the next point, which is 0.5, plus 4 times the function value at 0.75, and then the 1 on the end has no multiplier. Plus f at 1. So that's our Simpson. So it's going to be 0.25 over 3. And then plug 0 into our function. So you get e to the negative of 0 squared plus 4. Plug 0.25 in, e to the negative of 0.25 squared plus 2 e to the negative of 0.5 squared plus our 4 e to the negative of 0.75 squared, and plus plug in 1, which would be e to the negative of 1 squared. Square before you take the negative. Compute this in the calculator, so we can actually edit a little bit here. So I'm going to do second enter out in front here. I'm going to do an insert and insert a divide by 3. Well, that didn't work. So let's do a 0.25 divide by 3. And let's actually go ahead and insert some parentheses here. There's our 0.25 divided by 3 out in front. E to the 0 is our first one, and then this will be 4 e to the 0.25 squared, so I need to insert a 2 there. And then for my 1, it's going to be, let's see, I need to insert a 2 multiplier. There, and change my 1 to a 0.5. And then I've got plus a 4 e second of ln, and now this is a negative of 0.75 squared, and then plus no multiplier, second of ln, e to the negative 1, and that gets squared, arrow out, close our parentheses, 0.746855, so 7469. So that's to 4 decimal places. And they'll specify the number of decimal places that they want you to use. And I computed this using, you can do this with fnint actually on your calculator to check. So we can go to the math menu and then fnint, which is number 9. And we are going from 0 up to 1. And then we go ahead and put in our function, second e, this is negative of x, and it gets squared, and dx. And so full calculator accuracy, 74682. So our exact here, so e to the negative x squared dx was 74682 to 5 decimal places, We can see this was 7469, so it's only off by 1 in the 4th decimal place. There's some more decimal places here. But we can see that even with only 4 subintervals, Simpson's is actually very accurate.